Okay, so this week we're going to be moving up or down the chain of natural language. We have been talking about syntax and morphology. We're now talking about semantics. Well, you're probably thinking, oh great, we're now going to get the meaning of all of this stuff. The answer is not really. We're going to talk about how people in natural language processing deal with meaning and how we try to represent it. It's far from being a solved problem, and it's actually unbelievably hard. It's not clear what truth actually is. You would think that semantics should be really clear because, you know, it means something. Yeah, it means something, but we don't really know what that is. So there's actually sort of three things I'm going to be talking about over the next two lectures, and I'm going to try to get through two of them this lecture, but it might be that half of the second one moves on to Thursday. So I'm going to be talking first about how do we represent meaning in a symbolic way. So how can we come up with logics that actually represent the meaning of sentences and what desirable properties we would like for that. And then I'm going to talk about some of the aspects of how to get that information out of a natural language statement, and much more explicitly I'm going to be talking about what's often called computational semantics on Thursday, where I'm going to talk about how to be able to parse and end up with a parsing algorithm that gives you the meaning of the sentence rather than the just the syntax of the sentence. Okay? So, you know, last week we sort of talked about individual words. We talked about vector semantics. We talked about continuous representation, so big arrays of numbers that give a representation, and they're pretty good. We'd like to be able to do that for syntax, for sentences as well, but that's surprisingly hard, or at least it's very dependent on the domain that you're actually dealing with. And so you need to have lots of data in a particular domain to do it, or a super infinite amount of data for everything. But today we're going to be talking about meaning representation, and we're going to talk about how to be able to get that information and where is it in the syntactic representation. Okay, so some of these things are quite philosophical that I'm talking about. I mean, they are philosophical. They're part of the study of philosophy that you might think is something that is like, why do we care about this? The answer is, well, we do actually care about it. We're indirectly caring about what the people in philosophy care about meaning, and they've been thinking about meaning for a lot longer than we have, and therefore we can use information that's in there. So I'm first going to notice a distinction between intentional and extensional. Okay, so intentional means what is the actual meaning of a word. When we say a particular word, what does it actually mean? Okay, and so you can. This is very clear with proper names. When you say Alan W. Black, you mean this bearded Scotsman standing at the front. Okay, that's who it means. Actually, there's a few other people who seem to be using my name on the planet, although they probably don't think that they're using my name. They think I'm using their name. But when we think about that expression, it refers to me, and that's the meaning of that expression. Okay, so that's what it means. And so, if you wanted an actual function that would give you the meaning of a word, you would evaluate that function on the string Alan W. Black, and I would appear right in front of you because that's what it actually means. Okay, we used to have this as a homework. Okay, but I'd like to tell you it's a real pain because every time people execute that function, I have to appear, and so it's a lot of work. You know, running around Pittsburgh and appearing in front of computers at 2:30 a.m. to say I'm here. So we don't do that anymore. But that meaning, where you've got a string and you've got the actual physical object in the world, is what we mean by intentional semantics. Okay, now that's usually not what we want to do, because you don't really want to have a function that gives you the actual object. We're actually dealing with models in the world, so we're actually trying to get some representation. So what we really want is, when you evaluate Alan W. Black, you get the entry in Wikipedia for Alan W. Black rather than me, myself, because you treat that as what the meaning actually is. Alternatively, we can talk about extential representation. And that means it's what does the word refer to when we look at all of its actual forms. So we take the meaning of the colour red being everything that's red. So instead of saying it's a particular wavelength of light, we actually say that if everybody calls us red, then it's red. And so that's the definition. So we look for everything that's red, and it comes up with that. So in other words, the meaning is all the things that are being referred to as that. This is slightly easier to do computationally because you just look at the occurrence of a word and you look at all the things it refers to and you say, well, whatever it is the average of all of these things, and that's what our definition is actually going to be. Okay. Now that distinction between intentional and extensional, like how it gets used as opposed to what it actually means, might not seem really important to us, but it's sort of a choice on how we would go about trying to build computational models to try to do that. The extension one is much easier, okay, because what we do in our machine is we don't actually have to care about what real things are, we care about how it gets used, and in the context it gets used, we're using that as the meaning. And so that's easier to do because we can learn from data, okay? So if we're in some other language, we can still actually discover what it is. But let's just briefly say a little bit about colour. For example, across different languages, people have a very different separation of the colour space. So you might think that red is red is red, and it doesn't matter if you translate it into another language, it still means it's red. And the answer is actually for red it almost is true. But for many other colours, they actually change when you go into different cultures. So for example, I'll use my examples in Japanese because I know the language. So they have a word for blue, which is used for the colour of the sky. And it's usually translated as blue, aoi. But it's also, that colour is the same colour that the go light is on the traffic lights. Okay? And you might immediately say, oh, so the traffic lights have a blue light for go. No, it's the same colour as we get here. It's what we would call in English green. But they don't have a distinction between the sky colour and the go traffic light. Okay? There is another word, midori, that sort of means more greenish, but they don't have the same distinction that we actually have in English. Okay? And yet they go through life and make decisions about colours, and we are quite happy to accept them in their anime when we're watching them. So, it doesn't hinder them in any way, but we have a different distribution. Now, actually, if we get a little bit closer to home, and all the males in the audience are probably already saying, colours, yeah, I know all three of them, okay? While the women in the audience are saying, well, there's an infinite number of colours and it depends how you actually look at them. And in general, women have a much broader sense of colours than men, so we've already got distinctions for that. And you can have an infinite argument about whether the colour turquoise is blue or green, because, it sort of depends. And different English-speaking cultures have got different notions of that. But the point that I'm trying to build here is that the colour is not the intrinsic colour, it's actually what it gets used for to describe. Okay? And that's much easier to do machine learning with because it's really hard to know what truth is when you're doing computational semantics. We're going to look at ways of how to represent the meanings of words, verbs, nouns, okay, with respect to how they get used in actual examples and what their distribution is, rather than what fact or absolute fact is, because that's too hard to actually do it. Now, meaning representation languages have been studied for a long time. When I say a long time, I mean more than 5,000 years. And we still haven't really got it yet, because it's really incredibly hard. And although for certain domains it's pretty well defined, as soon as we get into things like natural language, it's pretty hard, because there's lots of nuances in natural language that are really pretty hard to actually represent in things like first-order predicate logic. So let's talk about what we would like that representation to be, the things that we're trying to get when we're talking about a meaning representation language. Okay? So if we look at a chart of the things that we've sort of been working on, we talked about linguistic inputs, strings of words, or speech, but we're not really talking about speech, although in a couple of weeks I'll be giving a few lectures on what the difference between speech and text is. We have results from parsing, or maybe we've got co-reference resolution. We're going to talk more about semantic role labeling. We're going to end up with the meaning representation, the logic, the thing that actually means something. Okay. What are the kinds of tasks that we deal with this? Well, answering SE questions on an exam, but answering question answers in a Wikipedia article is somewhat similar. Most of you are aware of that. Deciding on what you're going to do in a restaurant. When you're saying I'm going to eat at this restaurant, it means that eat and restaurant are actually part of the things that you're doing. Learning an activity from a bunch of instructions. If I say to a robot, go forward 5 meters, the meaning is moving the robot forward 5 meters. That's what's actually happening. That's the realization of the command, move forward 5 meters. Okay? But it might be more abstract things like making an investment decision, so it's actually making the decision to put your $10,000 on Red Hat, although that's probably too late. And then you have other things as recognizing an insult, which is surprisingly hard. There's lots of really easy ways to recognize insults. When somebody calls you an idiot, you probably know. But when somebody says, you're dressed nicely today, is that an insult or not? It depends how you're normally dressed. Okay? So these things are actually hard. But we want to have something that allows us to be able to evaluate and find out what the answer actually is. Okay? We would like verifiability in our representations. We like to be able to take the representation and check whether it's true. We don't actually care about the real world because we're computer scientists, so who cares about the real world? We don't actually care, but we want to be able to still be verifiable in the sense that we can check it in a database to see whether it's actually true or not. I mean, yeah, maybe we want the meaning of, open the gate. We want to find out whether the gate is now open, but that really means having a camera, looking at the picture and making a decision whether the gate is open or actually closed. But we'd like the representation to allow us to give us true or false out of it. Okay? So in other words, if we have a question like, does Udipi serve vegetarian food? We want a representation like in a query language that we can then put into a database and get the answer true or the answer false. Okay? Now, this is sort of not quite the same as whether this restaurant actually does serve vegetarian food. It really is we're comparing against some database information that's there. So let's be a little bit more specific in this space. So if we think about something like IMDb, IMDb is a database of all of the actors, all of the movies, all of the TV shows, and it shows the links between them, okay? And it's pretty good. I mean, it's good at the level that if it's not in there, people will say it didn't happen, and they'll actually believe the database rather than the TV show that it's actually in, okay? So it's pretty much truth, okay? But it's not really, really truth, in the sense that just because it's not there or that it is there doesn't mean that that movie actually has that actor in it. But that's sort of a definition of truth that you would do if you're saying, was Harrison Ford in Blade Runner? Okay, and the answer is yes, we're fairly sure about that, but we can use the database to go and find that information. If we know what a Harrison Ford representation is and we know what Blade Runner is, we can look it up in that database and we can get the information. Okay, it doesn't actually guarantee that Harrison Ford really is in Blade Runner, and of course it might be a replicant that's in Blade Runner who looks like Harrison Ford and not actually Harrison Ford, but we are not talking about real truth, we're talking about what our database says. And for most natural language processing, that's really what we end up coming down to. It's the computational representation of the world. It's often called the model of the world rather than the world itself. Okay? But we like to be able to ask these questions. We'd like our meaning representation language to be differentiable enough that we can actually answer truth questions about it. We'd also like unambiguous representations. Okay, so we take the sentence, let's eat somewhere near campus. Okay, most people are going to interpret that as, let's find a restaurant that's near campus and we'll go and eat there. Okay, but for those of you in the audience who are Godzilla, I don't think we have Godzilla in the class, I think they're in section B, but Godzilla may view this sentence in a completely different way, because Godzilla may think, I'm going to go to Forbes and Craig and eat the Starbucks building, okay? And so that's, let's go and eat somewhere, the Starbucks building, okay, near campus, okay? That's stupid as a way, but it is a valid interpretation of that sentence, at least syntactically, okay? And what we want when we have a representation of a sentence in natural language, we would like the meaning representation to know which of these two meanings it actually is. So we want an unambiguous representation of the meaning and not confuse the meanings of things. We're trying to separate them out. Okay? There's sort of another level of that not only we want one meaning, but if there are multiple natural language ways of representing the same thing, we'd like the same meaning. So if we have a sentence that says, Mad Max has vegetarian dishes, or they have vegetarian food at Mad Max, vegetarian dishes are served at Mad Max serves vegetarian fare, they all fundamentally mean the same thing, and we'd like the representation of each of these sentences to be exactly the same, or at least be able to give a distance metric between them that shows that they're basically meaning the same thing. Okay? So not only do we want unambiguous representation of an ambiguous sentence, we want multiple sentences that mean the same thing to map to the same meaning representation. So there's sort of two requirements for that. Trying to find a canonical form. There are also other things that we'd like to be able to do with our representations. We'd like to actually do some form of inference. So if we know X and Y, we can actually work out that Z has to be true as well. So, so can vegetarians eat at Mad Max? I'd like to find a restaurant where I can get vegetarian food. What we'd really like to be able to do is be able to get an answer out of there in such a way that we'd like to find Mad Max given this information. So this information says that Mad Max serves vegetarian food. That's what it means. And then if we ask a question where we want to know what X is, we can actually find a value of it being Mad Max. Okay, so that's variables. We'd like to be able to do, I'll come on to inference in a moment. So in the same way that if we have Delta flies Boeing 737s from Boston to New York, I'd like to be able to ask questions about which flights go from Boston to New York, who flies from Boston to New York, does 737s fly from Boston to New York, where do Delta fly Boeing 747s from and to. So I'd like to be able to ask these questions and be able to get the answers out of it. So this is inference from examples. So I have a bunch of examples and I can look them up and give answers of things that are missing. It's not just truth values, okay? Otherwise I have to ask an awful lot of questions to be able to find things out. I'd like to get some of the values out of the database as well. All of the work that we're talking about here, we're talking about literal interpretations. So actual, very concrete meanings of things. We're not talking about the metaphorical use of language, which surprisingly is always. Almost all language is metaphorical. It's amazing that anybody can work out anything that anybody says, because it's actually not common in normal language to use things literally. When we're talking to computers, though, we almost always talk in a literal way, and we don't use metaphors. So saying Ford was hemorrhaging money, okay, it doesn't mean that they were actually bleeding money. It doesn't mean that, okay? It means that they were losing money all the time uncontrollably, okay? And when you say, I could eat a horse, you don't want Alexa to say to you, searching for restaurants in the area that serve horse. That's not what it means, Okay, well, it could be what it means, but it's not actually what you want it to mean normally. So these metaphorical uses of things are not what we're talking about here. We really are fundamentally talking about literal interpretation of everything, because that's actually how people talk to machines. Okay, it's very common that they do that, and in fact we're sort of encouraged to do that to the extent that machines are so bad at metaphors that we don't actually get it to work. Now you should be aware that, as I said, almost everything in language is metaphor. So if you take a word like foot, okay, foot is the thing at the end of your leg, okay, and if you go and search the web for all the occurrences of the word foot and see what it refers to, you discover it almost never refers to the thing at the end of somebody's leg. It actually refers to the thing at the bottom of something, okay? So it's actually much more likely used metaphorically than it is used literally, okay? And that might be a problem if you're trying to work out meaning from data. You discover that actually metaphorical use is relatively common, and even for ridiculously common words, they get used metaphorically more than they get used literally. Okay? But here we're talking about literal interpretation, because that's the thing that sort of works, and the other thing is just incredibly hard. What do we want to represent? So in any domain, there's going to be particular things that we'd like to represent. So we're thinking about building a natural language system that's an interface to ordering pizza or getting buses or caring about flights or caring about actors or even caring about facts in Wikipedia. There's a bunch of objects that we're talking about, okay? And they're usually relatively concrete objects. So, you know, in the restaurant domain, there are things like the people, the restaurants, the cuisines, the type of food. We've also got properties of objects, okay? So we can care about the pickiness, whether somebody likes or dislikes things more than normal, how noisy a restaurant might be, the spiciness of the food, okay? I suppose the spiciness of the people could be true as well. But there are these properties of particular objects, colour, size, can actually make a difference. And you would like to be able to represent it. And we also have relations between these things, okay? And these relations might be things like serve. So we have serve, oishi, bento, and it serves Japanese food. So that's a relation about the information. So there's these objects, there's these properties, and we have relations between objects and properties. Okay? So that's the type of information we'd like to be able to get out of our meaning representation language. For most of these natural language things, language technology things, what we're really going to talk about is a knowledge base. It's fashionable to call it a knowledge graph these days, but it's really the same thing. It's just got more structure in it. So it's a big brown bag and it's got all the facts in it. Okay, they're sometimes in logic called axioms. You can think about them as facts. You can think of them just as entries in a database. You can think about them just as entries in a big flat file that's got the information in it. Okay, and importantly, we basically think that then our system knows these facts in a loose sense of the word know. We're not saying that it is at one with the concept of the facts that are in there. We're just saying it has a list and you can query it and get true-false information. You can search it and you can find information in it. Okay, so there's a database of facts. Okay, and we're querying it. We're getting information out of it. Okay, and this might be Google Knowledge Graph. This might be IMDb. This might be the thing that you built up for your particular pizza ordering system, but it has the information that's already there, and that's the world for your system. Everything that's in that brown bag is the world, and everything beyond that doesn't exist, because that's the only representation you have of the world. So if it's in that bag, you know about it. If it's not in that bag, it doesn't exist. It's not even that you don't know about it, it doesn't exist. Okay? So, what sort of meaning representation languages do we have on the planet? And the answer is almost an infinite number. for a long time, that's what almost every researcher in natural language process would do. They would come up with a new meaning representation language that would supposedly be better than all the previous ones. Logic, first order predicate logic, is one of the candidates that people keep coming back to, and the answer is it's sort of good, but it has problems. And so what you can do is you can actually take some representation of first order predicate logic along the top. First order predicate logic has variables, has objects, has relations, has predicates. It has two quantifiers, the existential ones, so this means the backwards E means there exists. There's also an upside down A for all, saying everything in this case. And you can get a representation for many things with this. You can really only do literal things. It's very hard to start caring about much more abstract things like time and sequence. It doesn't really work very well. There are ways to do it, but there are always limitations for it. But people have been trying to do first order predicate logic representations of the world forever. I mean, genuinely forever. Well, at least 5,000 years. And even modern companies are still trying to do that. There was a company in Texas, SciCorp, was doing this in the 80s, 90s, and even into the 2000s, of actually trying to model everything. When you look at what Freebase and the other one, I can't immediately remember its name. Oh, what's the other one? There's another Wikipedia-derived database. It's basically first-order predicate logic because that's sort of easy to represent facts in and some relationships between facts, but it's got limitations. Okay. So first-order predicate logic. So it's got functions which you can give a function name, and you can give it an argument, and it can return a value. So what's the dress code for the porch? It will return what it is, presumably casual. What's the cuisine for Udipi? Okay, presumably vegetarian or vegetarian and others. It might be a list of things. We have predicates which can be true or false. So Union Grill serves American food. Union Grill is a restaurant, so we have to identify that it has the property of being a restaurant rather than the cuisine or a person. Okay, and for many sentences there are quite good representations of first order predicate logic. So we can have things like have speaker $5 and not have speaker lots of time, which means there is a speaker that has $5 and doesn't have a lot of time. We have things like this, where this means for all x, there is if x is a person, then they have $5, which in natural language would mean what do you think this means in natural language?
All people have $5.
Yes. Okay, and so that's what it means, and that's not true in the real world. There are some people who have $10. Oh, I suppose they still have $5, and there are some people who have less than $5. But it means all x's that are people, all people. If they are a person, they're going to have $5. So it means all people have $5, which is not true. Yeah.
I feel like parentheses would help for like this next one, because it's like it's kind of hard to tell what's actually.
I sort of agree with you, but after a while you get used to reading it in the same way that parentheses really help in arithmetic expressions unless you're used to them. Okay, but there's no ambiguity here. Okay. But yes, you're right. Parentheses would probably help. Last one is there exists XY, person X, restaurant Y, and has visited, not has visited XY. So what does that mean in natural language?
There's at least one person X and at least one restaurant Y where the person has not visited the restaurant.
Yeah. Yeah. But do you think that's true? Yes, it must be true. I haven't been to every restaurant, so that's enough. So yeah, and so you can do this, but the types of sentences that have good first-order predicate logic representations are a little weird. They're the sorts of things that you would ask databases, which actually most of our sentences are not like that. Okay, so if you take some sentence from a newspaper article and take it, or from a book and look at it, it doesn't have a really good translation of the first order predicate logic. But in dialogue systems, especially information giving systems, they often do, because we're asking very direct things, very clear intents. We want to know the weather in Pittsburgh tomorrow afternoon. That could be translated easily. We want to know the number of US states that are bordered by other states who have rivers longer than 100 kilometers and have capital cities with populations less than 5 million. Okay, I don't actually think we ever want to know that, but that's actually the space that lots of people end up working with. And of course, we know that in the United States there can never be any rivers that are longer than 100 kilometers, because it would be in miles, it wouldn't be in kilometers. Sort of, for the most part, nouns translate to objects. Okay, so for first approximation, we're going to get, that's actually not what we're doing. We're having nouns actually being translated as properties. Sorry, you can do this in different ways. Properties, so in other words, restaurant gets done as something that's a restaurant. Okay, it's not a particular restaurant, it's just a restaurant, but you're going to have to try to identify it. Okay, adjectives correspond to one-place predicates as well, so things like vegetarian be true or false of a restaurant, okay, of an X, which X might also be a restaurant. Okay, verbs for the most part are one-place, two-place, or even three-place predicates. So we can have dine, from Noah dined. We can have eat, we have Noah ate American food, or we can have give, as in the bad sushi gave Noah a stomach ache. Okay, so it's transitive, intransitive, transitive, and ditransitive verbs identify the number of arguments that the predicate actually takes. Now, in logic, and one of the main advantages of logic is you can do what's called inference. So given some information, you can make predictions that are true from the information that you actually have. There is a particular form of inference that's called modus ponens, where if you have some fact that's true, or two facts that are true, you may be able to prove other things. These are sometimes called syllogisms, but the generic term for all of these is modus ponens. So here we have vegetarian restaurant of duty, and then we have another thing that all vegetarian restaurants serve vegetarian food. Okay, you might think that's obvious, but you've got to remember that the machine knows nothing about the symbols that are actually there. Okay, so being able to know that vegetarian food is in any way related to vegetarian restaurant is just done by these two rules, axioms. Okay, but if Udupi is a vegetarian restaurant, and this is true for the world that we're talking about, we can actually infer that serves Udupi vegetarian food. Okay, because we know that this is true for Udupi, and therefore we know that for everything that this is true, this is true. Okay, modus ponens is one of, depending how you count, 3 or 4 different ways of doing standard inference, and you can use them or not use them depending what it is. Modus ponens is the most common one, and the one that's most believed, or the one that usually works the well. And so you can actually then work this backwards. So what you can say is, if you want to know whether this is true, you can actually then look to see if there's anything that will show that that's true. Okay. First order predicate logic has advantages. It's pretty flexible for representation. It is very well understood. People have done PhD theses in this, and it is widely used. What they don't tell you on this page is, it's very easy to represent things that you can no longer prove in it, especially if you start including things like events or times or any form of modal representation. It actually doesn't really allow you to do that, and you can get into situations where you're trying to prove X and you don't know if you can prove it or not, so it's incomplete in the mathematical sense. This is a big problem if you really care about universality, but in real life it usually doesn't matter. So this is in the same type of way that we pointed out that context-free grammar doesn't actually cover everything in natural language that's generated by humans, but it's pretty good. And if you really have to care about the other stuff, then, well, you have to do something about it. But there's so much that you can do without caring about it that it's okay. And that's true for first-order predicate logic. There's so much that you can do, especially if the particular domain that you're dealing with has a very well-defined semantics. You can do first-order predicate logic pretty easy. Most dialogue systems are doing some form of representation in the first-order logic domain. But you can sort of relax it a little bit. Well, I don't know. Some people think this is relaxing. Some people think it's tightening it up. It's not clear what the direction actually is. But we can actually not have to care so much about predicate logic, particularly these exists and for all, because they're actually quite hard to interpret. You can come up with a thing called descriptive logic. And this actually makes it a little easier to do some representation. And there are lots of things like this. And often when you're dealing with dialogue and some question answer things, this is adequate for you to be able to have sufficient representation to be able to ask questions. IMDb would probably get away with doing things like this because you're very factual. There are almost everything's a proper noun, and therefore it makes things much easier to actually care about. Remember, we've been telling you often lots of different ways to do different things, and we've always said to you, you should use the one that's best for your the process that you're trying to do, for your particular task. So there's not, you should always use all of these things. It's like, here's a choice of things. Depending on what you're doing, use the one that works best for your task. Okay? And finding the representation language for whatever you're doing, you want one that's adequate, that's not too complex, that doesn't disappear into loops when you try to prove things, as long as it does the tasks that you actually want to do. And so descriptive logics are a little bit more restrictive than first-order logic, but they're often sufficient for dealing with well-defined tasks, which we often are doing. We may actually make a much stronger distinction between the two types of fundamental facts. We can, which round did we talk about? Oh yeah, the first one is about these general things about the world you're dealing with. All bistros are restaurants, all restaurants are businesses, where you've got these generic for all are being true. So there's sort of the generic rules within your domain, and then you have the individual facts. Okay, and for the most part, these ones will actually have quantifiers in them if you're doing it in first order predicate logic. Well, the second ones will not have quantifiers in them because they're all sort of proper names. And that distinction is quite useful at times. And so people sometimes call them T-box and A-box. I don't know what the T stands for. I think A stands for axioms, but I'm not 100% sure what the T stands for. But people use these terms all the time. I'm quite familiar with them. What we discover is that in our particular domain, there's not just massive objects. These objects themselves often have a related structure, okay? And that some of these are subtypes of other ones. And this is often called categories. So there's a category of restaurants, but they may actually have different types of restaurants. So we might have Indian restaurants, Chinese restaurants, American restaurants, and we might want to treat them as being similar but not related. We might have some rules that talk about something about all Indian restaurants, or we want to talk about something about all restaurants, but that's going to be true for Indian restaurants and American restaurants. Okay, and so we often talk about a relationship of subsumption. So we say the Indian restaurant is a restaurant. Okay, so this is subsumed in the subsumer, and having this hierarchy of inheritance where we may have facts about or information about restaurants that can be inherited, but usually facts about the lower one, Indian, may not necessarily go up to the higher one. we may actually end up with these forms that these sub-things might have an understanding that they don't have a relationship. We might have to say that Indian restaurants are not Italian restaurants. These ones are distinct, although I'm pretty sure there must be a curry and pasta restaurant somewhere. Seems so unlikely that it doesn't exist somewhere. But you know, in our hierarchy of describing restaurants, we might naively believe that there are distinct cuisines that do not overlap. Okay, which probably isn't true. However, we might also have restrictions that the hierarchy, so you can only go one way. So we don't say that all restaurants are Italian restaurants, okay? Unless they're in Italy, because presumably if it's an Indian restaurant and it's in Italy, it's still an Italian restaurant, is it? Depends on the definition. It's not Italian cuisine. And so we can have other levels of negation and disjunction on these. Often this hierarchy of relationship between us is very obvious, okay? Sometimes it isn't, and sometimes it gets very hard, but often it really is, and it's really useful for talking about your generic rules and your specific rules. You've got some notion of inheritance. If you've done object-oriented programming, you're probably already aware of this, and you're thinking, why do you have silly names for it? Well, we already have that. And the answer is it's the other way around. It's object-oriented stuff borrowed this from ontologies, as they're called in semantics. Okay, and this representation is very common. So ontology is the logic of studying the structure of objects in the world. But nowadays it basically means some knowledge graph representation. People at Amazon care about this all the time because they want to, for all the products, they want to be able to fit them into some particular category. They may be in multiple categories so that when people are searching they can find them in the right thing, but they have to make decisions about whether computers are electronics or not, and the answer is sort of. If you're asking about computers, then no. But if you're asking about electronics in general, you might include the computers, but you'd also include, you know, toasters and other things. So, what I've been talking about is the meaning representation. Okay, I've not been talking about how you really get that representation from the natural language. I've not been talking about that process of taking strings of words and getting first order predicate logic. Okay, that's what I'm going to talk about actually really on Thursday, but I'm going to continue here on being a little step towards that. So we're going back up to looking at taking the results of parsing and trying to extract information from it in such a way that we begin to get some notion of meaning representation. Okay. So, we're no longer talking about the meaning representation itself, we're talking about the strings of words, okay? And we're going to talk about this concept of semantic roles. It's not quite semantics, but it's pretty close and often is sufficient in order to be able to get the meaning out of it, okay? We've seen that grammar gives us some more information rather than a simple bag of words or even simple sequence of words, because there is structure that is in the syntax that is useful for knowing what the main verb is, what the actual subject of it is, which might not be the noun that's closest to the verb. Okay, so now what we want to do is, looking at that string of words, we'd like to be able to begin to get the information about what could be the predicate, what could be the first argument of the predicate out of it. And although this sometimes looks simple, I'm going to show, oh no, I'm sorry, it's going to be a little harder than what we want it to be. Okay? we've been talking about meanings of propositions and sentences which have a clear meaning, and now we're going to say, well, I'm going to take these big complex sentences, like you're going to get in Wikipedia, and trying to be able to get the information out of it, the particular main verb, and all of you have already thought about trying to do that within your question answer systems, and this is often called the predicate, okay? It's sometimes called the frame as well, and I'm going to talk about that as well. And the arguments to that predicate, okay, are often called roles. So there's a bunch of nouns, and they have some role with the predicate. They might be who actually did the eating and what was actually eaten, okay? But that role, how that object is used with respect to the verb, has a particular function, and we'd like to be able to identify what that is. Okay, so here's a bunch of sentences. Okay, Noah built an ark out of gopher wood. Don't worry, I have no idea what gopher wood is either, so we just assume it's some type of wood. I don't know, it's not important to the story. Many people read this as being Noah from the Bible, and I'd like to point out it's not. It's actually Noah Smith, who used to be a professor here, and while he was here, he actually went and built an ark. Okay, at least he told me that. He loaded 2 of every animal onto the ark. Really, Noah, you did that? But anyway, okay. Noah piloted the ark in stormy weather. Well, Pittsburgh is very clear, you could do it in stormy weather. When the skies cleared, all rejoiced. Okay, it's Pittsburgh, the sky never cleared. So that bit can't be true. But you've got the point that there's a little story, it's got a bunch of facts in it. Okay, and what we'd like to be able to do is identify this in a more simpler way that would allow us to be able to ask questions about the facts in this story. Okay, it's written in natural language, so we want to be able to convert it in some way to be able to do that. So first thing we might want to care about is the nouns. Okay, so Noah, it's a proper noun. You would hope that named entity recognition would get it. Probably would. Okay, but we have a he in the second sentence, and that's referring to the same Noah. Okay, and there's a Noah in the third one, so these little numbers are basically identifying which particular entity we're talking about. Okay, and we've got ark, and it appears multiple times, and we've got skies and all some group of people. Okay, we can talk about paraphrasing. Okay, basically rephrasing these so they mean the same thing. Remember what I said about meaning representation. You would like that even if it's written in a different way, the representation is the same. So you can then do some sort of distance metric about, are these 2 sentences the same? Is this a reasonable answer compared to what I think the answer should be, because they're actually talking about the same thing? So our original sentence was Noah built an ark out of gopher wood. We could also say an ark was built by Noah, it was made from gopher wood. It's the same meaning, okay, but syntactically it's quite different. Noah constructed an ark with wood from a gopher tree, so maybe that's what gopher wood is. I still don't really know what that is. I thought gopher was a funny little squirrely animal. But anyway, using gopher wood, Noah managed to put together an ark. Still means the same thing. Noah built an ark, okay. Sort of missing a bit of the information, but it's still actually. But we like all of these to be analysed in such that we get the same information. More importantly, we like to get the same predicate and the same arguments, independent of how it's actually the words are put together. Okay. In linguistics, semantic roles have been around forever. Maybe not 5,000 years, but probably 50 years, and they have particular names, and linguistically they have these somewhat awkward names at times, and they can be very hard to remember what the names are, and I never do, but I remember all the major ones because they're quite useful. And rather importantly, they're not about the syntactic thing. So we're not talking about the subject of the sentence. Okay, we're talking about who did it. So if it's something like built an ark, okay, Noah is the subject of that sentence, okay, but actually much more importantly, Noah is the agent for build, because it was Noah that did it. So when I say the ark was built by Noah. The ark's now the subject, but it's not the agent. Agent is now by Noah at the other end. And what we'd like to do, so in other words, what we're talking about is one is the syntactic position and the other one is the semantic position, the role. Okay? So the agent is the one that caused it to happen, the one that did it. Okay? So they've got to have agency, they're probably animate, they've got to at least be, you know, a human, they've maybe got to be an animal, or at least a Disney character that can actually move about and sing because they do things. Okay, although maybe the wind is an agent as well. It depends on one's definition, because the wind can close a door, and it didn't do it, you know, meaningfully. It didn't think, I'm going to close that door. At least we don't think that the wind can think. The patient is the thing that gets done by it. Okay, the theme is sort of the object, the force is the wind, and there's a whole bunch of special terms for it, and they are special. And people argue about which one's the best one. And I have to admit that some of them are pretty much magic to me. And I think if you're a non-native speaker, it's easier because they don't necessarily mean the thing that you would normally think they mean. And so you should go and look it up and find some examples, because it's sort of quite useful. It's always impressive when you actually say, oh, don't you mean the experiencer? Oh, yes, I do mean the experience. I don't know if I do mean it. But at least the first 5 you should know, okay? Because people are going to talk about that, okay? And so it's useful to actually have some form of it. So here's a random sentence, which I suspect perhaps my co-lecturer made the sentence. David threw the midterms from the Pausch Bridge to the hillside below. Okay? He didn't. They're in my office. He didn't throw them out. Promise. So David is the agent, because David is the one who did it. David is the one who's in control and is doing the action. Okay? The theme, the thing that's thrown, okay, is the midterms. Okay? And then what we have is they're going from X to Y, and this is called the source, and the goal. And so what we're doing is we're identifying these aspects of the frame as well. Okay, so we like to care about ultimately identifying these things automatically. Okay, so if we could identify these things automatically, and then it becomes much easier to actually try to write the first order predicate logic or whatever representation you would like to be. And so if it was the midterms were thrown from Pausch Bridge, then you can still actually get things, and we still are identifying the same roles independent of the surface level syntax. This is a philosophy joke, but you probably won't get it. Davidsonian was a form of a late philosopher from the last century, and there is a neo-Davidsonian philosophy, but I think this is actually Mortensen philosophy. So semantic role labeling is a task in natural language, like parsing, that people do all the time. You'll notice that Stanford one has it and NLTK doesn't. It's one way, I can't remember which way it is. Okay, that will take a sentence, okay, or possibly a paragraph or a document, so there's multi-sentence. And what it will do is for each predicate, each verb, okay, it will identify each of the arguments of that verb, so what they all are, okay. Sometimes you get told what the predicates are and you're trying to find out what the arguments are for those predicates. Sometimes it's just the raw text, okay. So semantic role labeling, SRL, is one of these tasks that we do in natural language processing. People compete on, people find better ways to do it. So predicates are for the most part the verb, although minus the tense. So Noah built an ark out of gopher wood. So build, an ark was built by Noah, so it's still the same form. It was made is our predicate. We have constructed, we have put together. All of these are predicates. Okay, you can think of it as the verbs. The arguments, okay, are the things that the verbs apply to. and we're trying to sort them out. So here we're color coding them, and so the agent is the reddish form, the theme is the green one, it's almost always the arc in this case, okay, and the gopher wood is the see, this is where I have to remember the name, the instrument, I think it is, that, you know, that's what the building was made out of. These are often called predicates and arguments, okay? In a technical sense of the word argument, you may have seen this in programming languages. That's where the term actually comes from. No, the programming languages got it from linguistics. These will differ, and there'll be different types of argument depending on the verb. So each verb has its own types of arguments that go with it. And so somebody has to list that somewhere, so you have to know what that is for particular verbs. So you have to look up a list, and I'll come to that in a minute. Because there can be things like, you know, John broke the window. We know that the agent was John. Well, we have the window broke. It doesn't specify that John did it and ran away, and we don't know who did it. So we don't know that John did it, but we still know the theme of what actually got broken. And there will be different variations of this. Different senses of a verb may have different sets of arguments. Okay, so it can get quite complex, and people spend a long time arguing about what the best definition of the sets of arguments actually are. So I said you've got to get a list of the verbs, and you've got to find out what arguments are actually there, and that's tough. Okay, and people discuss that, but it's okay because there's some data that some people have gone to try to find out what that actually is, and there's a thing called prop bank. So they took the Pentry Bank corpus, the same thing that we've been training our syntactic parsers on for years, and what they did was they went through and identified the predicates, and they identified the arguments for each. Now, originally they were going to name the arguments, and they discovered that, well, these people fought each other so much they all died, and so the second group of people came along and said, okay, let's not name the arguments, we're just going to call them 0, 1, 2, 3, 4, and not actually give them a name, and hopefully we'll have less arguments. Yeah, right. And so they're called arg0, arg1, arg2, etc. Though arg0 is almost always the agent type thing, the thing that is in the subject in the standard declarative sentences. And so this, and people were much more in agreement of this, because once you get typically about argument 2 or 3, people really never know what the name is, and they don't know what order they should actually be in. Okay, so in prop bank, if you look at the word agree and look at all of the occurrences of the word agree, what you discover, it's always got the agreeer. Okay, John agrees with me. Okay, John is the agreeer. Okay, the proposition, he agrees something. Okay, the world is flat. Okay, the other entity agreeing, because there can be lots of other people who might be at John and his friends. So you can have the group agreed. So that's the agreeer is the group. It wouldn't make an offer. Okay, so that's the proposition. Okay, and so you can have identifiable arguments. And within prop bank, not only is it looking at the data and giving examples, it's actually saying, here's the verb, here's all the arguments it has. So this is incredibly useful, because if we were setting this as a homework, you probably would, not want to do that. So here's fall, move downward, so in the sense of get smaller. The logical object, the patient, the thing falling, so the stock market fell. The extent it fell, so the stock market fell 50%. Starting point from 1,000 to 500. I don't know what the median would be for the stock market. There's not always these. Sales fell to 251 million from, so that's your from, etc. So it might be a percentage as well. And you might have, or the location would be something like through the atmosphere, if something is falling through something or fell through the water. So what we have is, for a particular sentence, we can actually try to identify what the verb is, and we can identify what the arguments actually are. They might not always be in the order of left to right, depending on what the syntax of the sentence is, particularly passive clauses. They're going to be different. There's another thing, apart from PropBank, called FrameNet. And FrameNet is sort of trying to do the same thing, but it said, no, we're going to name everything. We're not going to use arg0, arg1. We're actually going to name what it is. And what this means is you end up with way more frames than what you end up with in PropBank. So for a particular verb, there are a lot more different types of frames that you can actually have, because they're trying to differentiate between them. FrameNet is really hard to do. But again, what they did was they took the pen tree bank and they identified a bunch of verbs, and then they started labeling them and coming up with agreement. There was a group of about 4 or 5 linguists who've been working on it for some time out of Berkeley, and they were fairly successful considering how hard the job actually is. They never finished everything in the pen tree bank. It was too hard. Okay, the students graduated, so you had to find other students to do it. But it is another thing that's sort of the same thing, but it's much more detailed than what PropBank is. And it depends what you want to do, whether you want to look at PropBank or whether you want to look at FrameNet. Okay. So here we have, again, a bunch of different roles, and we identify them. And for each different verb, we're going to have some information about what arguments could actually be there, but we're naming what their function actually is rather than just giving them a number. Okay. FrameNet is surprisingly good. There are times it's just so unbelievably useful when you want to do semantic analysis. And the biggest complaint that people have about it is it doesn't have enough verbs in it. Okay, this isn't a full list of the verbs, but it's great for the verbs that we've actually dealt with, but if you want to use it for something else, it then gets really hard to use it because it just doesn't know any of the verbs you're using. So if you're trying to do, you know, a thing about booking restaurants, it just doesn't have these verbs in it that you have, and therefore it doesn't work anywhere near as well as analysing newspaper text. We had a PhD student here a couple of years ago where she used FrameNet to be able to try to predict what the objects were in a domain. So she would take unlabeled text in the domain and she was trying to discover the ontology in the domain by looking for objects that were in there that would fit within the frames identified by a FrameNet-based parser, and therefore she could build an ontology and therefore build ultimately a dialogue system talking about it without having humans involved. And that was pretty cool. She's now a professor at National Taiwan University, Vivian Chen, but she also worked at Google on the way, and I actually think that that's what Google is using in Google Home to be able to try to discover new things that people are saying by identifying the arguments in unspecified text. And this is a very fashionable area at the moment to try to do, because we have lots of raw data and we'd like to be able to understand what's going on, but we don't know how people actually refer to things. And so if you have all this data and you say, well, this is all the data, these are the things I can do, can I actually do a mapping and look at the distribution of it? And maybe you can actually do interesting things about when people talk to Google Home or Alexa and it doesn't work, what do they say next? Because they might say the thing that means the same in a different way. And if you can analyze that second one, maybe the one before meant that, and therefore you can actually do some analysis of this. There's a link here in the slides. I'm not going to go to it and give you a demo, and you can go and you can type in sentences, and it will show you what the verb analysis actually is. You can also look up particular verbs, and you can see what their arguments actually are, and it gives examples from the pen tree bank. It's pretty comprehensive. So how can we build a semantic role system? So I talked about what it is, but how could we go about building a system to actually do that? Well, you really need a parse, okay? This is not going to work without knowing what the parse is. And in fact, people who don't work in syntax, people who work in syntax think that syntax is the goal in itself. But actually, this is what syntax is for. syntax on its own doesn't really do anything, apart from maybe you can do some manipulation things or delete things. But really, the purpose of a parse is to identify what the main verb is and what the arguments to the main verb is. That's really what it's doing. So in other words, the reason that we have parses is really to be able to start doing semantic role labeling. Okay, and so what we can do is once we've parsed it, we can go and look for the predicate words, because we've identified the verb, we know what the arguments are. We can actually say, well, which particular form of the verb is it? We have to choose from PrupBank or FrameNet which one it is, and then start looking for the other arguments. We've got a potential bunch of arguments. We've got prepositions around them that allow us to be able to choose between them, and that will allow us to eventually get the semantic roles. Okay, and so if you use the semantic role labeler software in Stanford Core NLP, then that's what it does. Okay, it's actually not, well, yes, that is what it does, but it's now using neural stuff to label it for the second part. And the parser, I don't know, it might be using the neural parser. I can't actually remember. Okay. So that's it for today. I talked about meaning representation languages, so how can we get a meaning, and then talked a little bit about I'd like to be able to get the verb and its arguments and give them reasonable names and put them into the right order for that. What I'm going to talk about on Thursday is how to actually do what's called semantic parsing, where you get semantic roles and first order predicate logic for some of them directly out of the parser. So that's what it generates. Okay, thank you.